over different implementation of mutual exclusion guarantee. And this kind of problem, what are they? They are not just for mutual exclusion, but the mutual exclusion is a requirement, of course. But they introduce several more things. Here, you understand that the producer-consumer has some kind of communication. The producer find that, let's say the buffer is full, cannot produce, then they, because we will have at least one producer, that means that we can support more producer, as well as consumer, we can support more, unlike your pipe implementation in assignment 1, right? Yes, you should experience that, well, if you forgot to close some pipe, okay, then the entire pipeline program sucks and stuck in a particular point, okay? Now here is not talking about that kind of pipe. Another is, I talked about last week, this is about the crossroad puzzle, okay? I have a crossroad. That the crossroad, last time I showed it is a 4-way, and actually the implementation of this solution support from 3 rows up to infinite number of rows, okay? And we will talk about it, next week, next class, not next week, okay? And reiterate the problem. And last time I already talked about the semaphore implementation. Today we'll revisit it, because today we will see it in action inside code. And we need some revision over the operation of the up and down call, okay? So now, what is the producer-consumer problem, right? You already know about something because you are very close to the submission deadline, okay? If you don't know what is a producer-consumer or pipe, then you will have a big problem, okay? So you know about this. The producer-consumer is, now we understand that, hey, this LS is encoding something, and here the FIFO property, okay? And this is a bound buffer. So in your mind, please, if you have time, do a Google search or whatever, find the circular cube implementation. Okay? Now think about what is circular cube implementation. What are the basic implementations? You have a buffer, you have at least 2 integers representing the head and tail, right? And the head and tail will move so that you will keep track on the current, because the head can move and also the tail can move. So you will keep track on that. So the data structure at least is not just by drawing that buffer, but they're starting 2 extra variables, the head and the tail. Who don't know what I'm talking about? Yeah, then better Google search, okay? I cannot really drop you now, okay? So this is the basic construct. Now, if you understand this, then you will immediately find that, oh, you have a buffer, you have 2 variables. Let's say these 2 guys continuously try to produce or consume things. So you need mutual exclusion protection, right? When this guy tries to enqueue, you will touch the tail as well as the head, right? Because you have to compare the head and the tail, whether it's full or not. If it's not full, you will move the tail so that you will enqueue one more slot. And the reverse phase here happen in the consumer. The consumer will move the head of the queue so that you will consume one slot. And of course, you need to do a comparison between the head and the tail so that you know whether the queue is empty or not. If it's empty, it will flop. All right? Okay, do you understand what I said? Circular buffer implementation. Yeah, I hope that circular buffer implementation is at your stage. You can Google it and know how to write it. Okay, for ACM programmers, okay, ACM programmers contest people, okay, you don't need any assistant and within 10 minutes code it up, okay. For me, I can only talk about it, I forgot how to code, okay. So now, this base structure, you understand that you need mutual exclusion, that's why you need semaphore, right? Then I will introduce you one basic use of semaphore, we call it binary semaphore. The semaphore only switch from 0 to 1, 1 to 0, so it's binary, 1 or 0, and it acts as a lock over this big structure, okay? And this is the requirement. The requirement, I already talked about this with you guys. I think that you will forget about it because in your mind it's about the pipe, the close, the tutu, okay? And now the requirement is written here. I give you a very brief look over it. The red are the big points. Okay, let's say the producer. The producer only interested in whether the buffer is full or not, right? If it's full, it cannot produce anymore, so it will go to sleep for some time. But it's also interested in another status of the buffer. What if the buffer was okay, empty and it wanted to produce something? So does it mean that here the consumer may be suspended? Okay, so he will have the consumer should wake the producer up. Okay, if it sleeps, so this is vice versa scenario. Here you will find the producer should wake the consumer up. If this guy, the producer, finds something wrong, the buffer was empty. Okay? So in the reverse, if the producer find that, okay, the consumer find that when I want to consume something, it was full, then maybe the producer was sleeping because of this. Now you may ask one question, hey, can we implement something like maybe this producer or this consumer will detect the process status of the opposite side. Okay, in our design, we don't consider this. We don't consider a producer will look at the status of the consumer or the consumer look at the status of the producer. We want to leave this requirement because we may have producer-consumer doing other things, right? Maybe the producer want to produce something and then he want to go to sleep for 1 hour. Then the consumer cannot assume the producer state. If it is sleeping, that means that, oh, it is being blocked by the buffer. Okay? So we remove this assumption, not include that, I should say. And we do not allow these two guys to check their execution status. Okay? And let's say I have this diagram. This diagram is hard to see because it's just a film. Okay? So I will draw this up. All right, let's say we have two slots. Two slots, the producer and the consumer. Now you're very good at it, right? It produce character. Let's say I want to produce a ls, okay, and write, not invoke ls, write ls, okay, to the two slot there, okay? So we will write in FIFO way, right? But ls I also have enter, so 3 characters, okay? So when I try to produce, I will find there's a slot here, L, and then an S. So this is not a slot, okay? My bench right now. So what should you do, right? If you're the producer produce this guy, produce means insert in the buffer. Then here the \n is a fingering character that we cannot produce because I use up the 2 slots. So what should you do? You will go to sleep. Okay? Last time I talked about this case, I kind of carried some lies, okay? Actually, it's not in a suspended state. It's not in a suspended state. What is the exact state? Actually, how it writes things here. Okay? It is using the write system call. Okay? It is using the write system call. It's not using the enqueue call. There is no call for enqueue. And here, the consumer will use the read system call. Okay? So these two guys will just use a normal system call. And how the write system call, okay, be penalized, say that, okay, you try to write something, but here is using up the first slot and 2 slot. So how to penalize that, right? Very easy. The kernel don't let the system call to return. Okay? It just don't return. Just you call the write, I just keep you as a hostage. Okay, I jail the process within the kernel code. Okay, so this is the effect. This is not terminal stop signal. This is not a continuation signal. It is not about signal. It's about the read system call and the write system call itself. Okay, so any question about this number 1 point? I will use the write system call. Don't return it so that when they try to write the \n, okay, sucks. Okay. Right. What is the input? It's a /n input. Okay, it's just a face up. Okay, yeah. Write a /n, and this write call will get jailed. Okay, jailed. Jailed in the kernel. The kernel won't release it until when? Until this consumer start execution. Okay? So when the consumer start execution, in this environment, I don't talk about anything about mutual exclusion part. Okay? I just assume that the producer went first, and the producer find it is full, so it is being taken hostage inside the kernel. Now the consumer start running. We don't have any mutual exclusion requirement yet. When you run, the read system code will do something. It will try to DQ this guy, DQ, okay, and try to DQ this guy. And before you can DQ the S, when you're DQing the L, so this is DQ step A, it will check, okay, whether this buffer is full or not. If it is full, okay, so this is full now. So what should you do? The consumer, by invoking this read call, the read call now has some dark secret there. When you read it and find the buffer is full, will send kind of a signal. Actually, it's not a signal. Is to allow this producer to continue to write that new line character in. Okay? So now you remember this shot. I have to erase it. Okay, I erase that. Oops. This was sucks up. It's bad as Microsoft. Okay, so it was something like this, so you DQ it. And the write call of the /n now is successful. Yes, okay. Yeah, this slide, okay. You understand this is a Facebook tag, huh? So you now can write this /n in. Okay? Good. Then I will try to DQ again. So you DQ this, no problem, take it out. Let's say the producer won't execute, and this is a pending write. So let's say this pending write has successfully encoded here. So I can encode the /n and DQ. And later, when I try to DQ more, there is no slot that have data inside the pipe. So the read system call can no longer read anything, and it will be taken hostage inside the kernel. The kernel won't let you to return just like the keyboard input. Just like the keyboard input. You don't type anything, then the read system call will return. Okay? So this is the pipe implementation as you can see from your assignment 1 as well. Okay? If you want to know why your assignment 1 don't let you to return, let's say that someone tell me that, oh, cat, okay? And suddenly no, not cat. ALS cat, okay? ALS cat won't die, maybe we need a dog to kill it, right? No. It's because what? Because you have multiple guys monitoring those ends, okay? Multiple guys, what are the multiple guys? The parent, okay? I don't know, child A, child B, child C, I don't know how many child you have, okay? All monitoring those ends, and as the kernel knows that, oh, there are someone monitoring the ends, so I shouldn't close it. I shouldn't tell the other end and say, oh, no one care about the input anymore because all input have gone, so I won't let anyone encode anymore and tell you EOF on the read side. Okay, but this is not about this lecture. Okay, and this lecture we have this animation. The animation, because of the space requirement, I cannot put down so many details as I have first used the board to draw it. Okay, so the details are not that, but it's colorful, right? Yeah, so many colors. Yeah, you can go ahead and read it by yourself. Okay, so now it seems to be quite good, right? We have a kernel implementation. We don't need to care anymore. The pipe seems to be safe. Of course, it's safe. But according to your assignment experience, when we have multiple opening to the pipe with multiple processes, it seems sus. How sus it is. Yeah, it seems that you don't know how to close, you don't know how to read, so on and so forth. And as a matter of fact, the pipe never expect multiple people pointing to a particular end. It's always assumed that there is one guy pointing to it. So when a kernel pipe is used by multiple people on one end, that means multiple producer or multiple consumer, it don't know how to do it. Okay? So we need special implementation. And a special implementation, we will use semaphore. So that's why I say that I will go back a few slides before in order to explain to you how to bring about the mutual exclusion and what we call process synchronization. What is process synchronization? It means that you can use semaphore to set up some protocol. The protocol means that some steps, okay, some agreement over the processes. And this is the code. It seems to be some encrypted things, okay? What are they? Such a small program, 12 lines, and it's already a multiple read, multiple write scenario. Okay, so I will explain one by one. First of all, for the lines not highlight, okay? Not highlight things, this sucks, okay? Just produce an item. You can treat it as you try to input something from the keyboard and produce it to the pipe, okay? Then the other things is while true, it doesn't matter. And here, I highlight the remove item, okay, but not highlight the consume item just to make it generic. What is generic things here? Remove item means that I will touch the data structure, the shared data structure of the circular queue. And here, after I decode it, I don't care what I've done. I will try to consume it. Maybe the consumption takes 1 hour. It doesn't matter. Okay? I just want to make it generic. So the produce is not putting the same level as the insertion. I just separate it. Okay? So this produce the insertion. Here's the removal of the queue as well as the consumption. Now, what are the colors? The colors, again, same coloring code. When it is red, it is a section entry. When it is green, it is the section exit. So here means that it is something not important. Now it's something important. I hope that we have something, expanded, but I should go to sleep. Then I will be jailed here. My process will be jailed in the red part, so that I will go to sleep. Let's say I'm the producer here. I produce up to the number of empty slots. Then I will sleep in this area, and in the meantime here, this guy, the producer, the consumer will, based on the red line again, one of the red line will cause suspension. Okay? And now we will go into the pink part. The pink part is change of data structure. So you will expect that it's being protected by some semaphore here. So what are they? They are semaphore data structure. Okay? Now the green part is the exit. The green part will also touch the data structure, and the data structure, when you try to change it, it may wake up its partner. Okay, say this is the up call. Now I will revisit down. I know that because today's is deadline, so no one gets attention. Oh, what is the new tab? What is the down? What is the up? I will go back a little bit. Okay, go back a few pages. Come back to here. Okay, so here I introduced you the concept of binary semaphore. Okay, what is the binary semaphore? Binary semaphore usually has an initialization value equal to 1. So as in this example, so it's by initialization value, but I use a pointer. So I say, that means that I suddenly find that I shouldn't use a pointer, but it's okay. So it's equal to 1. Then what else? Then I will try to put it into the down call. Now, if you don't understand the down call again, we can go back a little bit. The down call is actually have a special slip here. If I found that some people change their binary semaphore from 1 to 0, and I am the second guy try to decrement it, so it is changing from 1 to 0 now, and I am the second guy. Now it is 0, I cannot decrement it. I will go to the special slip and put my PID inside this waiting list so that someone will look upon the waiting list when what? When the up call is being invoked. When the up call is invoked and it's kind of find that there's something wrong, right? What is the wrong things? it is originally 0. It may be there are someone jailed inside a special sleep, and it's look up this list to wake up the guys. Okay? So the up code and the down code work in the following way, and put together, you will have this. Let's say this is originally equal to 1, and you go through the red guy, and this is binary semaphore, so its initialization value is 1. It will change to 0, and you get the, let's say, it's kind of get lock. Okay? You get the lock, go into the pain part. This is your critical section, and the critical section, while you're in, other people cannot touch your critical section shared objects. So this area, until you release the lock, you will get into the trouble. The trouble is you'll find the semaphore value equals to 0. And you will get jailed inside this code. Until when? Until this guy changed the semaphore to 1. Now, we refer to the algorithm here, the classic producer-consumer algorithm. Can you find a binary semaphore? Which one? Which one is binary semaphore? Remember, usually binary semaphore, the initialization is equal to 1. So what is the variable name with initialization 1? No one find it? What is the name? MUTEX, right? Usually we don't call it MUTEX. We call it mutex. No S sound, okay? Mutex, just like LaTeX. Okay? LaTeX also has X but no S sound, right? It's called mutex. Mutex, mutual exclusion. Okay? Which means mutual exclusion. MUT, mutual, EX exclusion. So you will find this name appear many, many times. This mutex actually look at the code here. Look at the code here. If you ignore other down call, other up call, just focus as the mutex. Just focus as a mutex. What do you find? You will find always start with the down of the mutex, and then critical section, and then up the mutex. Can you find also here in the pattern of down the mutex, and then critical section, and then up it again? Okay? So this mute, yes. F what? Oh, later I will explain, don't worry. Okay? So this mutex is for mutual exclusion. Now you understand why. It starts with 1. Let's ignore these two guys. Ignore these two guys. I just treat it transparent, I cannot say it. Then with the producer inside the critical section, let's say context switching happens. The mutex, because you call down, it will become 0. And here, when you try to call down mutex, you cannot proceed. You will be frozen there until this guy called up mutex. So this is an interaction. And the feeling is mutual, right? This guy, this guy lock the mutex. You will exclude this guy from going in. Okay? So get a sense here. This sense is very important because I will use the same argument to explain to you what is the empty, what is the full. All right? Any questions? Any question over this basic news? If no, then I go on. Very important, huh? So if you don't understand what is the meaning, okay, I set up some questions here. If you are boring, you want to read ahead, okay, you can ask yourself this kind of questions. The question 2, I will ask you later after I understand the usage of empty and full. Okay? So question 1, we explained mutex just now. How are these two guys? Okay. Mutex here. Skip. So go to empty and full and empty. Now, what are they? It seems a bit strange, right? This guy say that down empty but up full. That is, it's not equal to the mutex case, right? I down the mutex and up the mutex. Down here is down the empty, up the full. Here is down the full and up the mutex, up the empty. Okay? But it seems to be strange. Now, what I'm trying to tell you, imagine here is the producer. Only the producer will execute. Okay, I didn't start the consumer. I didn't start it. I started 1 hour later. I just start this guy. Look at it. What is the initialization value of empty? What is that? And then for how many iterations this loop can go on before it gets blocked? Yeah, I hear the answer. Others, can you get my idea? This loop is a while true loop. While true loop, it will go indefinitely, but because we have this down call, this down empty call, you will change it from n from like 100 or 10, whatever you want to say. You will keep on decrement one by one, until when? Until you reach 0. Okay? Now imagine what is the control here. Can you imagine what is the control? Say this insert item is the enqueue operation of the bounded buffer or circular queue. Then what is this down control? No one get it? It's controlling the number of free space or empty slots in the buffer. You have one empty slot, you initialize it with 1. You have 3 empty slots, initialize it to 3. Then you produce 3 rounds, 1, 1, equivalent by 1, round 2, 1, 3, and the 4th round, you cannot proceed. Get the idea? Yeah, there's no animation. Too hard for me to create animation for this algorithm. Okay, so I know it's boring, so next time remember to bring coffee. Okay? Yeah, I know this. You guys want to do the coding. I know so many efforts is facing me now. Okay? Yeah, I should take a picture. So, but this is important as well, huh? So you will keep on decrement it and you suppose the slot. All right. Now, think about it. If this is the control of the empty slots, can you tell me what is the control of this? The down full. I choose a bad name, okay? What is the down full call? Yeah, discuss with your neighbor. I give you 1 minute, and tell me what is the control of this down. Imagine, you can do an imagination here. Let's say I reset the whole scenario. It's not this producer start first, but this consumer start first. I start the consumer first, the producer start 1 hour later. Then what will happen? And after 1 hour, this guy start working. What will happen? Talk with your neighbor. Yeah, I give you 1 hour. No, 1 minute. 1 minute only. And 1 hour, then you do coding. Yeah, there's a quite important control. And after you know it, you'll find this algorithm is very easy. I also make some drawing. And while you talk, I make drawing. All right. Okay. You seems to be like the talk, huh? Yeah. Sucks. Okay. Good. All right. So we have this case. Producer start first, and consumer start first. Producer start later. Okay. So if you have been talking about it, you should be able to answer this down. What is it? Should be what? Should be the full, right? So if it starts with the down full, can it proceed? Can it proceed? No, it cannot proceed, right? It cannot proceed. Why? Look at the full here. Full is 0. Initialization value is 0. Okay, if you can remember, refer back to notes. Yeah, this is 0. Okay, I highlight it. Okay, good. This is a deeper blue here. Okay, so it's 0. So I cannot proceed. So this guy is not happy. Yeah, this is my drawing. I always say that my art subject always fail. So accept this is sparring, not a sparring base. Okay. So then, what should you do next? You have to wait, right? Wait for what? Wait for the producer to start. The producer doesn't start, you cannot proceed because you are being jailed, and when it will help you. Alright? When the producer help you, take a look back to the code. Back to the code. The producer will try to help the frozen consumer. Is it this line 6? Line 6 help to wake it up? Yes or no? No. Which line? 7, 8, 9, 10. Don't tell me 11. Okay. 10. Alright? The 10th line will help to wake this guy up. Okay? Why is that? Very easy. So you have the down call. The down call is empty. What happened today? First free state there. So it will become 99. Alright? Then execute something. And then up. What is that? Up the full. Okay? So change this 0 to 1. Now remember upcall. The upcall property is like this. If previously the value is 0, you will shake this guy up. So that this guy is not unhappy now. This guy is quite happy. Okay? Quite happy is executing. Alright, so this guy is start executing, then it will have a chance to go inside its critical region. But the beauty of this design is so careful that I wake you up by using the up call. Doesn't mean that you can definitely go into the critical section and look at here. After you can pass through this full, all right, I wake you up by calling up full. This guy now wake up. You are not guaranteed to be going in there because you have another checking, but this checking is less strange. Not very strange. This check, what is that now? We call a little bit. This is the mutual exclusion check only. So within this 12 lines of code, you will find this. The design is so compact. The inner pair of the up-down semaphore is just a mutual exclusion check. And you won't find any variable to control the buffer size. We use semaphore to represent the buffer size. The buffer size starts with the empty slots equal to n, and you can produce for n rounds, and then you get suspended because you don't have enough empty slots. So I call it empty. And at the same time, you are not just decrementing an empty slot, but kind of producing, right? You are producing occupied slots. You keep on incrementing the occupied slots. And here, the consumer now is consuming, not just the item, but consuming the occupied slots. If you cannot consume it further, let's say the consumption bring this number into 0, you will be suspended. Okay? So the control is very beautiful, I would say. Just like make it, okay? And this is doable in all kind of programming language, no matter you're using Java. Java has wait and notify. You can implement this model using wait and notify. C++ and C will use prefix. Okay. What other models that you have heard of, or languages using concurrent control? If no, then later on we will share with you the prefix programming. for the wait and notify, sorry, if you really know what is that, ask me, okay? I used to be a Java tutor, okay? I know how to write a wait and notify threading program, okay? So this is the #1 question only. I explained to you what is a full and mutex and the empty semaphore. They range to you different control. One is for counting, right? I mean a pair, sorry, not one. A pair of them for counting. One is for binary semaphore, so the protection over a particular area to guarantee that only one guiding goes in. Okay? Second. The second question is more interesting. The interesting part is this kind of programs allows you to work together with different processes, but you cannot write in a bad form. You cannot introduce any bug by what? By interchanging two lines of code. Okay, so what I skip here is the explanation. You already heard of it. The explanation is here. Okay, and the properties I already mentioned it's called process synchronization. Now, what I'm doing here, can you see it? Before, after. Okay, can you see what is the change? Let's say there is a careless student, really careless. He tried to memorize the program, but while he's reading it, maybe he is also playing LOL. So he interchanged something. So interchanging these two statements. Oh, interesting, huh? Let's say you're interchanging two printf, still okay, right? In your assignment 1, you interchange two close statements, still okay. You interchange two down statements. This is okay. Ask yourself. I give a hint to think about it. What happens if I allow this interchange to stay there, and I let the producer to run first for 1 hour, let's say, and 1 hour later, I introduce the consumer. Can you imagine what will happen? I give you another minute. You talk with your neighbor to understand that, hey, what should be the producer look like after 1 hour? Suspended? Not suspended? If it's suspended, because of which statement? Yeah, go ahead. This time I won't draw it, because I have a drawing in the PowerPoint already. Which statement causes it to stop? It should be stopped, right? All right? How many people think that it will stop? It would go forever. Wow, causing the thermal go to the -1, -2, -3, right? No, not happen, right? It will stop definitely. To which statement? Yeah, previous case we stop at the statement down empty, right? We keep on incrementing the empty, and when the empty reaches 0, I will stop. Now, is it still holds? Does it still hold? Is it always because of the down empty get caused the suspension? This here, for this example. We think that is yes. It stopped at the new line 7. Okay, only a few. So others means that, oh, it's a repetition point, right? Yeah. Yeah, the new line 7 causes stopping, right? Causes the suspension. Because it's the only player, right? The only player, then no one will challenge him by occupying the mutex, right? He is the only player to play with mutex, so it's so boring that it keep on a decrement it from 1 to 0 and change back to 0 to 1, 1 to 0, 0 to 1. Now ask yourself, when the down call over the empty causes suspension, it's values to 0, right? How about the values of mu-tech? What is that? What is the value of mu-tech if the down call gives you suspension? What is the value? So you do 1? No. 0? The thing is 1? No. How about 0? Only a few. So then let's assume it's 1. What 0? 0. Okay. So now, if you understand this, then I will give you the animation. The animation is simple, right? You keep on execute. Let's say I change the n equal to 10, and then I will call something interesting. The news line 7 calls the suspension, and with the empty equals 0 together with the mu-tech equals 0, now happy ending coming. What happened if I introduce consumer? Will it try to consume all n's products? Or it will go to suspension for some reason? What is the status of consumer if I introduce consumer now? It will execute down full. So why full is equal to n? Because after the previous n rounds, I will up the full mu-tech so that the full mu-tech will change from 0, increase by 1, increase by 1, increase until I reach n. So will this down full cause suspension? No. How about this down mu-tech? Yes. The down mu-tech will cause suspension. Why? Because mu-tech is equal to 0. Then what will happen? Very interesting. Both will sleep forever. Forever and ever, happily together again. I mean, not again. It won't come back, okay? Both go to sleep. And this is a very famous scenario. We call it deadlock. Okay? Or someone don't call it deadlock. They have a very nice name. It's called deadly embrace. Yeah, deadly embrace in Cantonese. It's a perfect translation in Cantonese. I'm just to say. Embrace, right? You know what is embrace? Embrace is this. Okay? And you guys hold together and die. Deadly embrace. Okay? I'm just to say. Yeah. By changing 2 lines, then you have deadly embrace. And the deadly embrace can clearly illustrate it using this diagram. This diagram clearly, very clearly describe the scenario. I cannot find a human. Okay, no human will take this, right? So I cannot find a human, so I replace it with a dog. Okay, the dog is, should be a human. The human in there, he don't want to come out because he needs something. Okay, he needs toilet paper. Okay. And this guy needs the toilet seat with the holding of the paper. Okay, so what is the scenario? The scenario is very interesting. We have 2 shared resources. Each of them holding one. Each of them holding one of them. They won't release the resource until they get both. When they get both, they will release it. Understand what I mean? You can go in the toilet together with the toilet paper, then you will release both resources eventually. But without the both resource, no one can proceed. And this scenario is more interesting that none of them will release the resource. Will you release it? No. No. If you release it, you will afraid that you cannot go in again. This guy, will you release it? No. Think about it. After you use it, without the toilet paper, will you go out? I won't. Okay, I personally won't do it. Okay, I don't know what kind of paper I have. I need toilet paper. Okay. So this are the useless paper, right? This is the deadly embrace problem, and usually this is because of multiple resources. And our scenario here for the deadlock is something like this. This is a very high-level description. You may not think in the way that I described. So, the producer is actually, before it goes to sleep, why it goes to sleep? Because it needs something, right? But before it goes to sleep, It is holding the mutat by holding it down. Okay, I know that you don't remember the code. The code is here. It holding the down the mutat, so it's holding the mutat. When it holds the mutat, it tries to take this mutat together to go to the toilet seat. Yes, the toilet seat is not available. Okay, this empty is not available. It's already go to the empty. So, okay. So it cannot proceed and go to sleep. And in the same time, this consumer actually holding the chance to release the producer by up the mutat. It gets a chance. But before I can call up the mutat called empty, I need the mutat, which is not available. Okay? So we form a cycle here, the resource request cycle. I want this, okay, I'm holding this, but I want this. I'm holding this, but I want this. So form a cycle here, and if you don't understand the cycle, you can find the same cycle happen here. Okay? So this course is very easy. Whenever you don't understand something, yeah, go to the toilet and think about it, then you will understand this. Okay? Of course, you need the notes together with you when you go to the toilet. Okay? Or you, what is the code? I can't remember. Then you have to release the resource and take the resource again. Okay? So this is a deadlock or a deadly embrace. And this is not the end of the IPC classic example. The classic example, the algorithm is very easy for the producer consumer. Okay? Which control two things: mutual exclusion of the buffer, and this is not the buffer, also the head and tail pointer or integer. I don't know what you want to use, but let's say the integers. The whole data structure, you need to protect it. And at the same time, you need to chop between these two guys through the semaphore. So we set two semaphore so that both guys can guess, oh, maybe you are suspended. Okay, let me rescue you by calling the up. Now, I know this time is up. Okay, we have the next. The next is called dynamic philosopher. Okay, you can plan ahead. Okay, I know today is the deadline. Okay, you may not be interested in planning ahead. You can plan ahead to understand the scenario. The scenario is very easy. There are 5 professors. Okay, this is not CSCI professor, of course. Their work is think, eat, and sleep. Very, very easy, right? Think. After thinking, is get hungry, is eat. After eat, of course, sleep. And no need to go to the toilet, okay? And while it's eating, okay, because the problem is coming from the Western world, okay, so it's a fork. I will call it chopstick, okay? You need 2 chopsticks, right? Don't tell me that you can eat spaghetti with 1 chopstick, huh? I never success, okay, using 1 chopstick to eat spaghetti or noodles, okay? So each professor needs 2 chopsticks to eat. And assume that university is very dangerous, the spaghetti supply is infinite. Okay? And the professors sit around this table. Infinite supply of spaghetti, but only 5 chopsticks or 5 forks. They need 2 forks or 2 chopsticks. So at most, how many professors can eat together? At most 2, right? At most 2. Which 2? Okay? This scenario is very interesting. You can read ahead by yourself. You will understand that, hey, the 2 professor is not chosen at random. You have certain pattern. And this is a 5 professor scenario. We can reduce it to 3, to 4, or expand it to 1 million. It still works. Okay? And the code itself is very horrible. Let me jump ahead to the code. The code is like this. Separated into 5 components, okay? And each component has its own, own complex construction here, okay? So you won't find too many things that you understand. So next lecture on LSK, remember, go to LSK ground floor to buy coffee, okay? I expect the room is full of coffee smell, okay? And we will explain this solution. and together with one more solution over the database problem, the reader to the writer. Then we will finish this part, okay? And I will tell you how to implement this code using 3 threads in part 6. All right? Class dismissed. See you later.